Welcome to Stats with Chaz. I'm Dr. Charlie Collins. Today I will discuss the sampling distribution. The sampling distribution underlies all inferential statistics and allows us to draw conclusions about the distribution of a sample. It links the population distribution to the actual sample statistics theoretically by way of the central limit theorem. I'll talk about that in a minute. Today we will cover the sampling distribution in more detail, the construction of a sampling distribution, and the central limit theorem. Alright, before we examine the sampling distribution further, let's revisit variables for a minute. We know that in order to adequately describe a variable, we need the shape of its distribution, a measure of central tendency, and a measure of dispersion. We know we can get all this information from a sample of the population. But what allows us to link our sample to the population is the sampling distribution. The sampling distribution is the theoretical probability distribution of a variable for all possible samples of a certain sample size. Alright, let me translate. Suppose we know the shape of the distribution, mean and standard deviation of a population. We know this is not usually the case, which is why we use samples, but let's just say we know this information. What the sampling distribution does, theoretically, is randomly selects cases from that population, let's say 100 cases, but it does this an infinite number of times. Given the number of samples of 100 cases drawn from the population, we know that there will definitely be some samples that do not represent the population characteristics. For example, there may be one sample drawn where all 100 cases fall on the lower end of the distribution, and another sample where all 100 cases fall on the higher end of the distribution, and even a number where the sample is highly skewed. However, taken together, all of these samples create a distribution that is normal, with a mean and standard deviation very near the population. Two theorems help us understand why this is the case. The first theorem states that if repeated random samples of a population are drawn, the mean and standard deviation of the sampling distribution will be very close to the mean and standard deviation of the population. So these numerous random cases are our theoretical sampling distribution. The second theorem, called the central limit theorem, states that if repeated random samples of a population are drawn, the sampling distribution will approach normality with a mean and standard deviation near the population mean and standard deviation. In addition, as our sample gets larger, the closer it comes to the sampling distribution. The central limit theorem is important because it removes the need for the population distribution to be normally distributed, meaning it can be skewed. As the number of samples increases in our theoretical drawing of samples, their accumulation will create a distribution that is normal and not skewed. This is due to the randomness of the sampling distribution. You may be asking, how does this relate to our direct sample then? It allows us to assume that the sample should be normally distributed with a mean and standard deviation near the population's mean and standard deviation. And if our sample does not fit this criteria, we can make assumptions about the effects from something like an independent variable on our sample. If this all sounds a little obscure, you're not alone. This one is kind of a brain twister. What to take away from this is that the sampling distribution, which is a theoretical distribution, allows us to assume that the larger our sample size gets, the closer it should get to becoming normally distributed with a mean and standard deviation near the population's mean and standard deviation. This allows us to examine potential effects from external variables on our sample. That is all I have for this talk. By now you should know the sampling distribution in a little more detail, the construction of the sampling distribution using multiple samples, and the central limit theorem. Thanks for watching Stats with Chaz. I'm Dr. Charlie Collins.